So we have proved this Berdych-Simonovich theorem, which determines the asymptotic behavior of this extremal function for Rn. And it's a quadratic function, which is with constant multiply this, and then some lower order term here. However, I mean, this is not so useful when your graph F is bipartite. And R is 1, this one is 0. So what it says, and this one has what? No edges, 0. So what it said is just that this function is subquadratic. We don't know how fast it goes, and we don't know the asymptotics of it. So for that reason, the extremal number for bipartite case, I mean, they are called the degenerate case of the extremal number, degenerate extremal number. So we want to consider this degenerate case. And for this bipartite graph, we don't have one unifying theory which give you the extremal number of all those graphs. But later we have to find one by one. We have to use add-on method to deal graph by graph. In fact, we don't really know much on the extremal number of bipartite graph. Most of the bipartite graph, we don't know its value. And there are only sporadic cases we know. One of them is complete bipartite. So Kovari and Shoshtran prove a upper bound on the complete bipartite graph's extremal number. So given S and T, let's say S is at most T, then we can prove the upper bound on this extremal number, which is at most T times n to the 2 minus 1 over F. Oh. So let's prove this. How do we prove this? What's this KST? So let's say you have K3, 4, then this K3, 4, how do you find it? You want to fix 3 vertices, and then you want to consider its common neighborhood. And in this common neighborhood, if you find the 4 vertices, then you are done. So that's roughly what we want to do. So let's see on n vertex graph with at least T times n to the 2 minus 1 over S edges. And let B be the vertex graph. And for all vertices, what you do is you choose F vertices from its neighbor. So, okay, so maybe what I said could be a bit misleading. So that's what we want to do. So we want to find F vertices because common neighborhood is large. But we want to compute it from the perspective of these vertices. This vertex is related to all of them. So it has many edges. If you choose S of them, that's potential candidate for this choice. And you add them all, and what? It says, what I mean is that the size of it. Then that's same as the degree choose S. You add it for all the vertices. So here, what we know is that this function, x choose S, for fixed X, if x choose S is a convex function. Say fx is x choose S is a convex function, which is also defined. This is not only defined for integer, but also defined for all real number by letting this as the function. And this is convex function. And what do we have? From convexity, we actually can prove this inequality. So what do we know? Say 1 over n times the f of x1 to f of xn is at least what? The f of 1 over n x1 to xn. That's the convexity. So that's what you get from convexity. So you apply that, and then you move this n here, then you get this inequality. So now you have this. From Herzog lemma, this is twice times the number of edges. So this is n times 2t, at least 2t times n 1 minus 1 over s. So it's that. This is what? At least this for large n. That's t times n choose s. Then what do we know? By Pigeonhole principle, so that is the number of choices for all sets of size s. And here what we have counted. For each vertex, you choose a s vertices which lie in the neighbor. Then for other, you count it again. For other, you count it again. And if some s set is counted many times, that means that for that s set, you have many choices of these vertices which are adjacent to all of them. So that means there exists a set S of size exactly S, which belongs to NP for at least what? T choices of this vertex. Does this give a copy of KAIST, which finishes the proof? Okay, so this gives us the upper bound. And what do we have to do to get the lower bound? For lower bound, we have to construct a graph which doesn't contain KST, but has many edges. And yeah, that's more difficult. So in order to determine this extremal number, we need the upper bound and lower bound. And lower bound, we need to construct such a graph. But in general, here, we don't know whether this is some constant times n to the 2 minus 1 over s. So this is something we don't know. And this constant could be depending on t and s. We don't care. I mean, mainly our question is whether this exponent is tight. We don't know that. But for t, large t, we know. So, 폴라로니아의 따보 in 1996 proved that if t is at least factorial plus 1, then you can actually construct an example of graph which contains more than this many edges, some constant times this many edges, and having no KST as a subgraph. And later, Arun Gonyai Sabo improved it to slightly better bound. So instead of s factorial, you take s minus 1 factorial. But for smaller one, we don't know. On the other hand, we actually know for very small case, K22 and K33, we rather know the value very exactly, but I mean, I don't want to specify this the error term, the smaller term, but the leading term is again determined. But for other complete bipartite graph, we don't know much. Okay, give me a moment. Actually, yeah, I forgot to mention one thing, that this was further improved by book very recently in 2023. That if t is bigger than some constant times 2ds for some constant c, then this is also type. Okay. But okay, let's then discuss about some lower bound. So one of the way to obtain certain lower bound, which is not as strong as possible, I mean not as strong as we want, is to use the progressing method. Okay, before that, let me point out that every bipartite graph is subgraph of certain KST. So this provides an upper bound for all bipartite graphs, but in general, this is not type. We can consider progressing method to find the lower bound for each bipartite graph. For example, here, when we consider a complete bipartite graph, and there exists N0 such that following holds for all n bigger than 0, that there exists an m-vertex graph C with the number of edges being bigger than this kind of is not so important, but let's say 1 over 5 and then to the 2 minus 2 over x plus 1, which does not contain this KSS as a subgroup. So we can prove this using this progression method. And then here, this number is not as ideal as what we wanted here, but at least this provides some rule. So what we do is we consider a random graph on the vertex set. Bracket n with its hair being on edge with probability, say p, which is n to the negative 2 over s plus 1, independently at random with this probability. So now again, as we want to construct, we use probabilistic method to show the existence of certain construction. And now we have to consider the bad events, which give you a KSS as subgraph. So for a fixed pair, A, B of disjoint subsets of bracket n of size S. what is the probability that this AB induces the complete bipartite graph. And you have S partitions that are S square pairs. So the probability that it gives the complete bipartite graph is P to the S square. Now what? We use deletion method, the alteration method. Let X be the number of edges in this graph, and let Y be the number of distinct copies of KSX. Then what? We use the linearity of expectation. We can consider the expectation of X minus Y. X, you can easily compute. Each pair is included with probability P, so it's P times N choose 2. And this, you have to sum up this P to the S pair for all possible choices of A and B. And what? This is what? This is at least half times N to the 2S divided by 1 over S over 1. Okay, technically this is a negative n term, so let's say 1 over 3. And then this is what? We choose or set A by edge S manually, and then in the remaining one you choose S vertices for B, and then AB and BA give you the same copy, so you divide by halves to get this. Then you can see that this is what? You can prove this. Okay, and then you just plug in this C. Then if S is what? At least 2. So you can easily check that this is at least this. Hence, there exists a choice such that X minus Y is bigger than 1 over 5 and to the 2S divided by X plus 1. For such a graph, what we do, we delete on H from each copy of this KSS. Then what we obtain a graph, an inverse graph, X graph with at least 1 over 5 times N to the 2 minus 2 over S plus 1 edges having no copies of KSS. Okay, so we can use this progression method to get a roll bound, and which is versatile in the sense that you can apply this method to any bipartite graph. But the downside is that it doesn't give you tight bounds. On the other hand, there is this ways of using algebraic technique to gain a lower bound on the extremal number. And this algebraic technique is powerful so that it sometimes gives you a tight lower bound. However, this is not as versatile, so that this only applies to very specific graph. So, for example, what is applied is K22, and K33, and these, they use the algebraic technique. Here, I mean, he used the algebraic technique and probabilistic technique together to get this result, and then other are using algebraic technique. And also there are several more known extremal number for cycles. So one can actually show that this upper bound for all k equals 2, but for lower bound, it is known only for k equal 2, 3, 5. Again, these groups are all, this lower bound are using something called algebraic technique. And then we will show you the algebraic technique for this K22 case, which happens to be the same as C4. So for infinitely many, okay, let's not do this. Let's say for all large n, there exists graph with n vertices and with half minus 0 over 1 n to the 3 over 2 edges containing no copy of C4, or maybe let's write K22. Right. So in order to show this little one, let's say let epsilon be a small number. Then what we can do, we know is that for large n, there is this prime number p between say 1 minus epsilon times q root of n and q root of n minus 1 thing. So there exists a prime between these two. So this is a strengthening of Bertrand's postulate. Bertrand's postulate is that for any x, there is a prime number between x and 2x. And even stronger statement, this holds. Actually, it's a even stronger statement holds. For any large n, between n and n plus n to the 0 point some number, which I don't remember, which is 0.6, say. I think the best known is 0.5 something. Anyway, in here, there must be one integer, one prime number. So for large n, this is true. So anyway, so we know that there is this prime number in here. And we consider field of character P, then take a tuple, and we only consider the non-zero tuple. And we say that A1, A2, A3, and B1, B2, B3 are equivalent if and only if there is this K such that K also in this field. Such that Pi is KII for each I. So basically you take a projective. Okay. So A1, A2, A3, and K times A1, A2, A3 you identify. So that bracket A1, A2, A3 is the equivalent class. Containing this A1, A2, A3. Okay, now what? We let B, which are the vertexes of our graph, is collection of these equivalent class. So we consider G the graph on the vertex B, where two vertex are adjacent if and only if A1 B1 plus A2 B2 plus A3 B3 is 0. Then what happens? For a two distinct vertices, U, A1, A2, A3, and then B, which is B1, B2, B3. If some other vertex X, Y, G is adjacent to both of them, then what happens? A1 X plus A2 Y plus A3 G equals 0, and then B1 X plus B2 Y plus B3 G is 0. So both of them hold. But these two are distinct. As UV are distinct, we know that the set of points in a P cube satisfying its equation, I mean both equations, they forms a line. So this is space, and then one such equation, the dimension goes down. So this is plane, and then you have to satisfy another equation, then that's a line. But this, what's this line? As the solution, define a single equivalent graph. This line is passing through 0, 0, 0. So this is single equivalent graph. This is one point. And there is this unique common neighbors of U and B. So G does not have K22 as a subgraph. Okay, then what? G has P squared plus P plus 1. You can check that many vertices, which is at least 1 minus epsilon squared n vertices. We just add some isolated vertices. To make it n vertex graph. Then what? What do we know? Every vertex here, we can check that every vertex of this G, which is not isolated vertices, is adjacent to exactly P minus 1, no, P plus 1, which is at least 1 minus epsilon times square root of n, other vertices. So number of edges is at least what? Say some half minus root of 1 times n to the 3 over 2. I mean, this you can write it as the expression of epsilon. But anyway, so you can prove this. So in a sense, this uses the algebraic property that in a projective plane, if you have two lines and they meet at exactly one point, then each line is a neighborhood of one vertex, and then neighborhood of one vertex. You define it so that the neighborhood of one vertex is a line. And two lines has only one intersection, never two, so you don't have K to 2. So essentially, other algebraic techniques are, in a sense, you use this kind of algebraic and geometric property. So this is using line and line intersection is only one, not two. That's how we did it. And here, what you do is roughly, you take a sphere, and then sphere, and then sphere. Three sphere, then their intersection is, if they are in general position, their intersection is at most 2 points, never 3 points, right? So that's the geometric intuition. And then use that in an algebraic way over, good case, you prove it. Of course, that's not trivial. This is just intuition, but how you translate into algebraic way is difficult. And these are more complicated. They consider large systems of linear equation, and then use some algebraic fact that if this holds, then there are not many solutions, etc. So that's roughly how this kind of algebraic technique can be applied to get a lower bound for the extremal number. Okay, so we have learned about the extremal number of bipartite graph. And so far we have just talked about the existence of certain graph in terms of number of edges. But we can also ask the question on how many. If number of edges is above this threshold, we know that it guarantees one copy of triangle, or one copy of KR, or one copy of KSS. But how many can we obtain? So we will briefly discuss about that in the next video. Okay, thank you for listening. I will see you next time.